Better for 1D?
Yeah, you would solve for the hydroxide ion here. This would be H.
Okay.
This would be
For problem 1D, and that is what is the pH after addition of 100 mils of base? And what is this condition? What words would we use to describe it?
Equivalence.
This is the equivalence point. And so this is the equivalence point. And let me get the door. Okay, at the equivalence point, all of the acid has been deprotonated. So we've added an equimolar amount of base, deprotonating all the acid, and we have generated what is equivalent to a solution of sodium acetate. You want me to prop that?
No.
Oh, the light. Good point. Hadn't thought of that. So we've generated what is equivalent to a solution of sodium acetate. And effectively, we're going to have to deal with the fact that the acetate ion, being the conjugate base of a weak acid, is strong enough to do what?
Wait, say that again? Yeah, what?
The conjugate, the acetate ion, being the conjugate base of the weak acid.
So it's a strong, that makes it a strong.
It's strong enough to pull a hydrogen ion, or not pull a hydrogen ion, essentially, off of a what?
Hydrogen.
Off of the water molecule, off of the solvent. We call it hydrolysis. So it's going to be strong enough to hydrolyze the solvent. And so that's generally true. The conjugates of weak acids or bases are strong bases or acids. But we're not talking about strength in the same sense that we talked about it when we were talking about the parent acid. In that sense, what were we talking about? Acid strength was
Disassociation in the water.
yeah, the extent that it dissociates. It's the electrolyte strength. Now we're talking about strength in another sense, and we're talking about it being strong enough to protonate or deprotonate the solvent. And so that's where that statement applies. That the conjugates of weaks are strong, and the converse is also true. The conjugates of strong are too weak to hydrolyze the solvent. So when we have a strong acid like hydrochloric acid, the conjugate base being a chloride ion is too weak to pluck a proton off of the water. Okay? And so now we end up with a solution of sodium acetate, or the acetate ion concentration. And what I've done is it's be the same thing as if I took the amount of moles of acetic acid that were present. So that would be that many moles. I've generated that many moles of acetate. And I just added 100 mils of water to it. So I've doubled the volume. So what is the molarity of the...
It's half.
Yeah, it's half the molarity. Okay? And so we're going to have that, the equivalent point, therefore, the acetate ion concentration is equal to the original. I'll put a little knot there to denote the initial concentration of the acetic acid divided by 2 equals 1.0 molar. And now we're going to have to find the KB for the base, for the acetate ion. And what relation am I going to exploit to find that? What's true?
KA times
KA is,
Yeah, the product of the Ka, for conjugate pairs, Ka and Kb is equal to Kw. So Ka times Kb equals Kw, and therefore Kb equal to Kw over Ka, and that's equal to 10 minus 14 over 10 to the minus 4.75. And what do the rules of the exponents have me do?
Subtract.
Subtract. Well, I subtract
Return to
minus
the
minus is plus, so it's minus 14.
9.25.
Yeah, equals 10 to the minus 9.25. Now, should we check the approximation?
Yeah.
Why not?
This is sensuous thing. Since
Yeah.
you was here anyway, might as well. Okay, so we'll do that. And approximation was, what is it again? How do I check that?
Molarity over KA.
1.0 divided by 10 to the minus 9.25. Well, that you can almost, by
Yeah.
inspection, that's going to be awful close to, because what is the log, or what is
9 trillion.
what is 1? It's 10 to the 0. So I have 10 to the 0 minus a minus 10 to the minus 9.25, and so the minus becomes a plus. It's going to be 10 to the 9.25 equals 10 to the 9.25. Well, that's pretty close, about 1.5 billion. Is it 10.25? No, because it's 10 to the 0 there. Yeah. It's 10 to the 9.25.
We're okay.
And that's a billion, which is significantly larger than 100. We pretty much knew that up front because when we started, this was true.
Right.
It's going to be even more true now, but yeah. About 1.5 billion is much bigger. So, actually it's around 1.8 billion. Now we have to write out the equation for the hydrolysis. And this is why you're going to have to know, to answer the question that was asked earlier about, you have to know the conjugates. Yeah, you have to know what the conjugate base is for this reason, because I'm going to write out the hydrolysis equilibrium, and that is, I take an acetate ion, aqueous, plus water, and it's in equilibrium with what? What's on this side?
H3.
HOAC, it's acetic acid, aqueous plus
OH.
hydroxide, thank you. Okay, so we've got now a basic, a weak base equilibrium, and we're going to hit the ice with it. What goes here?
1.
Here?
0. Minus 6. Plus 6. 1 minus 6.
So we've got that expression, and now KB is equal to 10 to the minus 9.25 is equal to x squared over 1 minus x. And what's the approximation give us?
X squared over 1.
X squared over 1.
X squared over 1, which happens to be equal to x squared. X squared. Okay, and therefore x is going to be equal to 10 to the minus 9.25 to the 1/2 power. Okay, and what are the rules of the exponents have me do? I divide by 2. So on my scratch paper I go 2 into 9.25 is 4.6 25. 10 to the minus 4.625. Just a little bit. And so 10 to the minus 4.625 is equal to X, which is equal to the hydroxide ion concentration. And now there's several different things we can do at this point.
The POH is 4.62.
Yeah, we immediately can find the POH, and then finding the POH we can,
Find the
so,
pH.
so yeah, we can use in which relation. There's several
We can
approaches.
use negative logs, or we can use
Yeah.
the KW.
Yeah, yeah. So we can take that, we can simply subtract it from
Yeah.
14, or I'm going to do it a different way because
Yeah.
the easiest way we'll talk about, and I recommend you do whatever you find easiest. They're all equivalent. In this particular problem, what I would want to see on the detail, obviously I had to move this down to another board. I would have said, you could have said X equals this equals hydroxide and done it on, so I had to repeat this. I would recommend repeating yourself on the test. And now, therefore, well, no, I'm going to take this following approach. That's hydroxide ion concentration. Now let's take into account the fact that Kw, for all time, this equilibrium is the equilibrium of the solvent, which is thermodynamically coupled to all the equilibrium processes involving hydroxide ion and hydronium ion. So this one's my favorite, but it's going to be equivalent to just simply finding POH and subtracting it from 14, which we can, I'll talk about in a minute. So therefore, the hydronium ion concentration is equal to Kw divided by the hydroxide ion concentration equals 10 to the minus 14 over 10 to the minus 4.625. And so this reveals why it's these are all equivalent to the same thing. I can take the pKw, or pKw is equal to pH plus POH. That adds up to 14. And so I can then subtract the POH from 14. I'll get the same result. But I like this particular approach because this reveals the underlying autoionization equilibrium of the solvent and how that is thermodynamically coupled in this fashion. And so now I have to, on my scratch paper, what are the rules of excellence have me do?
Subtract.
I subtract.